All right, so today we're going to be talking about our controller board architecture as well as our driver controls. And this won't be really long of a knowledge share, so a bit different than usual. And let's get started. So agenda today, we're first going to talk about the controller board and its design, and then just have brief basics about CAN and the structure of that communication. And then we're going to talk about the different parts of driver controls, which is our way of interacting with the vehicle as a driver while it's operational. Cool. So to begin with the controller boards, just to walk through the design, we use the controller boards are found on every PCB that we use that needs to interface over CAN. And this is because every one of our controller boards is basically a CAN node in our network. And so the microcontroller we chose to use for our controller board, and this is what brings our like gives us our digital logic. It's our main interface for all of our protocols. And we chose the STM32F072CBT6, and we actually went over this controller board back in week 4, just because we were looking at data sheets. So if you want to learn more, I guess, about what exactly the controller board gives us and its specs, definitely look at the data sheet, or there's definitely information from that knowledge share if you're curious. But really the main reasons we chose this controller board is because it had enough GPIO pins that we could use. It was able to interface over, I believe, about 2 I2C buses, a SPI, UART, and other low-speed protocols that we need for our communication. And it has a CAN controller. And of course, this is important, us being an automotive vehicle. CAN is the standard protocol. And we'll get into why it's so useful in the next slide. But that's another reason we chose this particular microcontroller from the STM32 series. Another thing that the controller board really gives us, and you might notice from all of the boards that you guys have been designing or looking at, that we have a 3v3 voltage reference that we're getting from our controller board mezzanine connector. And what the controller board itself has is that LDO on it for the 3v3 reference. And then finally, a major component of our controller boards is a CAN transceiver, the TCAN33-2. And why this is important, the CAN, okay, so the controller board will be able to have a CAN controller, right, which is basically 2 pins, an RX and a TX pin, that control or give single-ended communication back and forth. But then what's needed for our network to really work is to have this kind of CAN transceiver. And what it does is it takes that single-ended RX-TX and it converts it to the differential signal that CAN is with the CAN-H and CAN-high and CAN-low lines. And so, just to really walk through the schematics, let's do that for the controller board. And if you look at them, they're not way too complicated. We have the receptacle Bergstack connector that we'll have the mating pair for on every board that uses the controller board. And there's always improvements for this board, and one of which is that it usually in designs that use a connector as a structural member, which we do, it might be nice to have another connector on the board so that it's always stable and not kind of wonky as it is. So for a future revision, that might be nice. But in any case, all of these signals we want to bring out to any board that has a controller board sits on this connector. And then this is just a debug header with some UART lines and SWD lines. And then we have our CAN connectors. So if you look at the 3D version, there are these 2 guys, and we need to have these connectors so that we are able to continue the network and reach all of the nodes in our CAN. And then we actually get to the sheet with the microcontroller, so our STM32. And this has all of the outputs that we're taking from the board. It also has our 32 megahertz crystal with some loading capacitors that go and feed into the input of the crystal pins on our microcontroller. As well as we have some indicative LEDs that we have just assigned to some of our GPIOs, and it gives us indication of functionality when we put on the controller board. And then finally, as I mentioned before, we have our TCAN CAN transceiver. Again, when we're looking at the microcontroller, CAN is routed out as an RX and a TX pin, but then to match with the differential signaling of a CAN protocol, we need the CAN transceiver to deal with that. And then again, as I mentioned, we have our 3v3 converter. So this is it. And actually, I said it was an LDO. It's not. It's a buck converter, which just gives it a bit more efficiency. So let me let that slide later. But cool. These are really just the main components of the controller board. And now let's really talk about CAN basics. So CAN is the standard for automotive serial communication. And the way it works is kind of, you can see in this diagram, there are different CAN nodes. So every one of our controller boards is a CAN node essentially, with the MCU being the microcontroller. And then we have the CAN controller, which is just a part of the microcontroller, which deals with that RX-TX lines. And then we have our CAN transceiver. And this is what really, it makes it a differential signal that goes through the CAN high and CAN low lines. And just, I know we've talked about differential communication before, but just to better understand it, the way that differential communication works is it looks for a difference between the two lines, and after a certain threshold, the difference will result in a high versus a low. And so another really important thing to know about CAN communication is it's a message-based protocol. In I2C, as you might have heard from before knowledge shares, it's an address-based protocol. That is, a message is sent to a particular address, and if you're the component with the address, you respond to it or you react somehow. CAN works in the way that a message is always sent from the transceiver both ways down the CAN-H and CAN-L lines. And so it's based on messages instead. And something else you might have heard of us talking about before are having termination resistors. And so actually we can see them here on our controller boards. These two guys. So the purpose of these termination resistors are that because CAN is a protocol that will allow communication to flow both ways, it will, sorry, there is a comment. Let me address that. Chat. God, it's not opening. Oh, okay. Yes, so the termination resistors, they're on the controller board. And the reason they're needed is because CAN is a two-way, communication flows both ways. And so for keeping the signal integrity, what needs to happen is that at the endpoints of our CAN lines, there has to be these termination resistors so that they can absorb the energy and not be reflected back into the CAN line. So there has, like the name says, they have to terminate the communication. And that's what their purpose is. And 120 ohms is almost the standard for long traced impedances on the, terminations on the CAN traces. And that's just because that's the standard impedance you would be expecting in your long CAN traces. So that's why you see 120 ohms, and that's why in our design, we have 62 ohms, well in series, so that gives us our 120 ohms. And you'll notice this termination resistor, it absorbs the energy from both lines, and it just sits in between. Cool. And by the way, sorry.
Just to note for the terminations, they are only populated on two.
Yeah,
the rest are all removed.
Yes, as Micah just said, which I was about to just say, by the way, they're only existed on the 2 boards that are on the endpoints of our CAN lines. Every other board has them depopped. Okay, cool. And if there are no questions about kind of just CAN basics and how we use it, we can move on to the driver controls boards. So driver controls, again, this is a mock-up from Adrian of, or like a diagram of all of the front interface that we have as a driver. And the key areas that driver controls deals with is the buttons here on center console. So you have a hazards, park, reverse, neutral, drive, as well as on-off. The steering wheel. So you have all of the inputs that you're getting from your steering stock, as well as the buttons on the wheel itself. And then you have the brake and accelerator. And so the angles that these make, as well as the angles steering makes, all of those are inputs into our driver controls. We have the necessity of the driver pushing any of these buttons or turning any of these stocks to somehow incorporate in the sequencing we have with our vehicle. And that's why it's important we get these input signals and then process them, as well as be able to communicate what we're seeing on our CAN network. And that's like the majority of how driver controls works. They're all boards that have CAN network node, as well as interface with the user somehow, or gain some sort of user input. And so this diagram on the right is like really essentially how every single driver controls board works. And by the way, the driver controls board split up into steering interface, pedal interface, and center console. So we get an analog or digital input, this is a button or a pot. And then what we do is we go through some sort of filtering or debouncing. And as you might have known from some of the tasks we've been pushing, which are the noise sources in the car, we've actually had many problems in the past where the noises that couple into the analog or digital inputs we get from our driver control systems will be affected to a point where we're not getting accurate readings of either. And so that's why it's really important that these boards, of course, sitting in a car, which is a noisy vehicle, have some sort of filtering and debouncing, which I'll explain a bit more later. And then all these signals, they enter a GPIO of sorts or go through an ADC. If it's an analog, a signal, GPIO, usually if it's a digital. And then they go through our controller board and enter are communicated through the CAN node that the board is. So we usually use, they usually use for the filtering and debouncing a combination of RC low pass filters and Schmitt triggers. And if they're analog inputs, we use the exact same layout where there's just an RC filter respect with a unity gain buffer. And if they're digital inputs, we have an RC filter again, but with the Schmitt trigger. And I'll walk you through all of those schematics next. But first, just to have a better understanding of what we're really looking for with these filters. So debounce, if you're unfamiliar with it, it's essentially when you have a switch and you press on it or close the switch somehow, there's this period of fluctuation in which the button from the vibration, or not the button, but the contact from the vibration of like hitting the other side will bounce a bit. And what debounce does is it takes into account these fluctuations you would get, which, this affects our value of low versus high. And so we want to be able to filter out these high frequency fluctuations to give us a very constant high-low change. And that's what debouncing is. It's the process of getting rid of this. And then noise sources are basically frequency components of a certain frequency that enter our lines or analog inputs or digital inputs and cause some sort of fluctuation in terms at a certain frequency. And so the way that we deal with that is with using RC filters. And so you might have learned about this a bit in class, but essentially RC filters use the property of reactance. It basically decreases with an increase in frequency for capacitors. So having the resistor capacitor configuration in a certain way will allow us to only allow frequencies up to a certain point with a low pass filter to pass through, and then high frequency components like something like this would not be able to pass. And we'll go through kind of the RC filters we're using, but that's the essential idea. So first board, pedal interface. What are its inputs? It takes in one potentiometer reading from the brake angle at the moment, and then two potentiometer readings from the pedal angle, as well as also a potentiometer reading from the steering angle. And so these are all the inputs, and what the purpose of getting these inputs are is that when we are going into drive mode, we have to know that the brake is being held down and we're hitting power. And so that will like make us safely transition from a off car to a on car with motor controllers ready to go. Another purpose of knowing the brake angle is for regen braking, activating it. And then acceleration, we base the what we're sending to our motor controllers based on the angle that we're pushing on our accelerator pedals, which again are coming from those two pots from our pedal angles. So cool. I can walk through the board. It's actually quite simple, and I think this is the first board I designed on this team, which is kind of cool to look back on. So essentially, it only has analog inputs, as you saw from that slide. So it's taking in on these connectors the two pots from the accelerator, the pot from the steering angle, potentiometer from the brake pedal. And then this is the endpoint, our controller board again. But first, what those inputs on those connectors will go through is the standard analog filtration system we have in play on driver's controls. So what we have is first it goes through an RC filter, as you can see here. And what this RC filter does is it attenuates frequencies, or the cutoff frequency is about 100 hertz. And that's because, we know that these are analog inputs. They're digital, they're analog inputs. They aren't high frequency components at all. So 100 hertz is like a good enough value to really get rid of all the higher frequency components. And then we have just the buffer for drive strength purposes. And then that goes into the output of this node, which then heads to our ADC. These are analog inputs again, so they have to go as inputs into our ADC on pedal, and then that digital interface on our ADC interfaces over I2C, which then goes to our controller board. And that's really a majority of the board. There's also just a 3VO power supply regulator. This one is an LDO that takes from 3V3 to 3V0, and it's used because our ADC references it mainly. And also something to just note, you might see a resistor and capacitor here, and you might think, oh, is that an RC filter? It is not. This resistor is simply for current limiting for the outputs of this buffer. And this is, again, just like a decoupling capacitor. You'll notice even if you tried to like find what the cutoff frequency is for this kind of configuration, it's like 0 hertz. And that's because, like you can see as well, this resistor is such a low impedance. It's not really there to interfere with the RC or make an RC filter with this capacitor. It's simply for the drive strength purposes. So cool. Walk through that. Oh, chat. What are 3VO sources for on the analog input schematics before the buffer amp? 3VO surface. Sorry. So this is okay. So our potentiometer is a variable resistor, right? Honestly, we could have used 3V3 for this as well, but we use 3VO, but it's essentially part of the resistor divider that will give us an input when we change the value of the variable resistor that's the potentiometer. Does that make sense? Nita?
Yeah, makes sense. Thanks.
Okay, cool. No problem. Cool. And then we can talk about steering. So steering, it's actually broken up into two boards. And the second board is quite simply a connector board. What it does, and just, you know, the way that steering kind of has to work because of the way it sits on the wheel, is that first, our steering board is essentially sitting behind here and is providing these buttons. These buttons we use for cruise control, push to talk, and regen brake toggle, and there are these buttons up here. But then there's also the fact that we need inputs from the steering stock. You know, a normal car, you have to put on your indicators when you're turning, and that's essential. It's not a button, it's usually the stock that you can toggle. And so what we have is that with the stock we buy off the shelf, we have a board that fits in to a slot in the stock, and it'll provide us the analog references for everything from the stock. And so this board literally just sits inside that slot, has a connector, and connects through to this board, the steering main board, that will provide its input paths. So with that, we could really talk about the inputs a bit more. From the stock, what we're getting is the turn signal, and technically high beam on off, as well as lane assist. I don't think we're going to use lane assist, but we're still like pulling it from that stock. What we have as buttons are the cruise control on off, cruise control increase, cruise control decrease, all separate buttons. Push to talk, and what this is for is that as part of regulations, when we have a driver, they have to have a sort of like hands-free way, or they have to be still like holding the steering wheel to communicate over radio communications. So the push to talk is for us to enable the radio when they have to talk. And then we have regen toggle, so we can turn off or on brake regen, and as well as there's a horn switch, but this is an input from a different switch that goes into the steering board. And so the purpose for all of this is obviously, you know, as a driver, you have to have controls and such controls, as well as everything is a very regular thing to have in the vehicle, but then the push to talk and regen, we kind of have to have separate, and it just is convenient to have these on the wheel. And then something interesting for steering and kind of the design of how it works, because everything sits on the wheel, but you know, the wheel is turning. So how do you have nice cabling? Because like if you were to just like dangle cables that would go around, as you turn your wheel, your cables would twist. So the solution to that is having a clock spring. And you might have heard us talk about this because we have to replace the ribbon cable in our clock spring. But the way it works is that there are two endpoints on either side. And as the cable turns, this ribbon cable like will essentially tighten or loosen, but it has enough length so that it wouldn't like affect it. And then we're able to route our communications over this ribbon cable around to the other side without having to deal with the problem that the cables will twist as the wheel turns. And then finally, oh, actually, I could just walk through steering as well, the project itself. So we have the controller board, that's standard. And then this is the connector that goes to the other board and where we get the 4 signals from. And then we have a push to talk button, which is connected to this connector and is a switch when we press for an input that we will route to our controller board. So this is just the steering stock connector. And the only analog input from steering, and this is the same exact filter as we saw on pedal, is that it is from the steering, the turn stock signal. And the reason it has to be analog is that your turn stock signal can be a right, a left, or a nothing, which are 3 different states, and we can't make it digital in that case. And then we have all of the button inputs. So all of the cruise controls that sit on the steering wheel board itself, as well as all of the buttons that will kind of sit outside the steering wheel board, which are like the horn button, and all the inputs we get from the steering stock, which are buttons. So they're digital on-off, which is fine. And so when we have a digital input, like a button, we have a different process of filtration, as I mentioned before. The first thing is going through the exact same RC filter, the 15K 0.1 microfarads, 100 hertz cutoff. And then what we have is another component called a Schmitt trigger. And to really briefly explain how Schmitt triggers work, as the name it implies, they are triggers of sorts. And what they work on is a basis of hysteresis, which hysteresis is essentially when you increase something over a threshold, you want to be able to only follow, or so let's just say you have a threshold at 3 volts as your high. So when you have a 3v3 input, you're able to have a logic 1. When you have issues with noise, that like 3v3 input, let's just say it varies between 2.8 and 3.6 somehow because of added noise onto the line. Because of that, if you just had it so that it was a normal like switch, this went into a controller board, you would be triggering a high and a low a lot of times when you clearly want a high value. So what a Schmitt trigger will do is after you pass that high value, it will lower the threshold from 3 VO for this case into something lower, maybe like 2.6, before you have a logic low. And so this really helps because if our analog or our digital inputs are being affected by noise, it will hold the value of high for as long as it's really affected by noise and until you actually want a value of low. And so as a trigger, it latches in ways to the digital outputs until you clearly are executing a low versus high on the inputs. And so this is pretty useful for us to have as part of the filtration for both the noise sources that go on our digital lines and our debouncing. And so that's why you see it for all of the button inputs. And then this is steering board, and I think that really summarizes the main components. So now we can talk about the last board, which is center console. So as you see, center console has this huge hole. The hole is for a fan because what you'll also notice is that center console mounts with the Raspberry Pi. This header that you'll also see on BMS Carrier it interfaces with the Pi header directly. And so this is the main Pi we use for all of our processing, as well as telemetry, I believe. And so this fan, because the Pi gets really hot, this is the optimal location for cooling, and that's why this fan exists. And so we can really walk through, again, what center console does. The center console, it has the following drive state inputs: neutral, park, reverse, forward, and just power on and off, as well as your hazards. Your low beam can also be turned on, as well as your DRLs. And you know why this is important is because we don't have a stick shift as you would have in a normal or in ordinary cars, I guess, or most cars. But instead we have these buttons that control a change in gear. And so with these inputs, the purpose of this board has multi-purposes, actually, more than just dealing with these inputs. It, of course, has the main car state controls that it gets as inputs, but it also, because these are really important switch or buttons and we like them to be fancy, they also have LEDs. This board will also control the LEDs on those buttons, as well as, of course, interface with the Raspberry Pi. And so for that interface, there's a bunch of other components it needs, like a 5-volt buck, an RTC, which I'll talk about, which RTC stands for real-time clock, and just the interface header. And of course, as I mentioned, the hole for the fan mounting to cool that Raspberry Pi. And so with that, the last part of this knowledge share is really going over carrier board design. So first, of course, we have the regular controller board. Something we might have to reevaluate for a next revision of Center Console is having these power headers, because I'm pretty sure we're going to want to control power for at least display. I'm not sure why it has carrier board power here, but for from power distribution instead. And then, you know, again, these are fancy buttons. So we get a variety of inputs. We interface the buttons, not just the reference value, but also controlling the LED for each button. And so that's what these headers are for, to interface with. And then there's just a few pull-up resistors or standoffs, other normal components that interface with our controller board and the connectors. And then, of course, the buttons, they go through our RC filters, and then the Schmidt triggers, as had been done on steering. And so that's what you'll see here. And then something kind of special with the buttons again is that we interface over I2C with an LED IO expander. Well, it's just an IO expander, but it's meant for the LEDs. And so we are able to enable different pins on this FET driver, which will drive the current going to the LEDs. And so that's how we interface with the driver and turn on the LEDs when you press the button. Like if you press the hazards, you want the button to show that you have pressed it. And then finally, this page is really for the Raspberry Pi interfacing. So of course, we have that header that we use for the Raspberry Pi. We have a regulator. This is a DC buck from 12 volts to 5 volts because Raspberry Pis, they use this reference mainly. And then we have an real-time clock. And why we need this is because Raspberry Pis don't have their own real-time clock. And a real-time clock is what deals with all of the timing for all of the computation on the board. And Raspberry Pis don't come with these RTCs because it's just expected that they will be connected over Wi-Fi or Ethernet to get that RTC value. But since we will be in conditions where we want the center console and everything to work, even when we don't have Wi-Fi and Ethernet, we have to add our own real-time clock. And this is just the suggested IC for Raspberry Pis, the PCF 8523 with the 32.768 kilohertz crystal for clocking. And then you'll also notice we have a battery here. And again, it's for the same purposes. You know, we always want this Raspberry Pi to be clocking. And so we have this 3V that we replace for the real-time clock whenever it's needed. And the real-time clock, it interfaces over I2C with the Raspberry Pi, which is why we pulled out these headers so that it can communicate that clock value. And yeah, that's really the main components of Center Console and driver controls. With that, I have nothing else to add. Does anyone have any questions? Cool. Just like an additional thing, you know, the filtration is really a big part of these boards. And we've like tested it. One of the first things I worked on actually was like the noises on our previous versions of all these boards. We didn't have like filters. So if you like even like communicate with the walkie-talkie near any of the boards and then scope the values you're seeing that would be entering the controller board, you could see like huge ripples on the analog and digital lines. That would definitely affect the signal you're trying to communicate. So it goes to show like it's really important that we know what kind of noise we see in our car and we're able to compensate with our filters correctly. Especially when it comes to driver controls, the driver should always have good handle of the car. So yeah, they're an important subsystem. Any other questions? We have like a minute left, so this is the first perfectly timed meeting. Okay, well, if not, thank you, everyone. And oop. Okay, I'm gonna end the call. Thanks.